questions and answers. Please do note down any questions that you would have during this presentation. We'd be happy to answer it at the end. But we're going to start off presenting our demonstration project, and I'm going to get we'll do a brief introduction about what this technology demonstration is, and then we'll get into the basic architecture of what we had set up here with the TRAK machine tool here to my left, to your right, how we accomplished real-time data collection, what we did with that data, and how we realized the benefits. So we're going to present all that. I'll do first half of this presentation, then I'll call up Danny, who is a PhD student at the University of Connecticut working under Dr. Farhad Admani, and he is going to present the artificial intelligence side of this and the how his algorithm performed, and then we'll get into seeing how we realize the benefits of that. So brief context. One of the things that, how do we realize when I say realizing the value of AI, of machine learning? In manufacturing, and for this particular use case, this demonstration, we're realizing it in corrective action control. So we machined a set of 23 airfoils, and during the course of machining those airfoils, we realized some variability during the manufacturing process. Variability affected the part dimension, right? So part 1 to part 23 had some variation in its dimensions. And what we want to show you is how we leveraged real-time data and artificial intelligence to predict part deviation as we were machining the part, and then how we use those predictions to apply corrective action control, and more specifically, how we communicated with the machine controller to apply changes to the parameters for the machining operation. So this demonstration is part 2 and a continuation from our first presentation in February, where we focused on digital thread and its value. And that was, as I mentioned before, the automation of production programming. Having your software solutions come up with the programs, the CNC programs, to produce your parts. Now we're going to get into, as I'm calling it, demonstration 2. Now we're going to get into how we control manufacturing variability. In this demonstration, this is the airfoil that we machined. We only concentrated on the blade surface itself and the side and the top of the platform. So what you're seeing here is the raw stock. It's about 1 inch, 1¼ inches in diameter, and it's about 3 inches tall. Just to give you a little bit of perspective on the size of the part. We have actually, to my left, to your right, on the table next to the TRAK machine tool, all of the 23 parts if you'd like to look at them up close. So for this demonstration, we used the Siemens NX-CAM to actually program the machining path. We used third wave to optimize that machining path, but more so, we actually looked at a particular function in third wave solutions, a product called Distortio, to calculate workpiece deflection. I'll talk a little bit more about that. Then we use Siemens Run My Virtual Machine, the digital twin of this machine, to not only validate the machining program, validate that we're not going to have any crashes, that we have the correct tool stick out lengths, but also to perform causality analysis. So I'll show you how we use that software to do that. And then, of course, the TRAK machine tool, the VMC10si, is the system with the 4th axis that Rob had mentioned before. That this is the system that we did this demonstration on. So the CNC operations, we have several. The first one really is a roughing operation for the tip, and it's really just to very lightly engage into the stock material from the tip inwards. Then we go into roughing the top half of the blade. Now, the way that this experiment was set up, we wanted to get into a circumstance where we would, be able to show you workpiece deflection at its maximum. And to do that, normally you would have constrained the tip of the blade. So the way that this is machined is the stock material is put into a three-jaw chuck on the machine. It's held in a horizontal fashion, so it's rotated about a horizontal axis. And the machine tool comes down in the Z direction. And normally you would have, the tip constrained so that as you're rotating the part, you would perform the machining with both the tip and the base, constrained. In our case, we left the tip free, but in leaving the tip free, we try to employ, machining strategies that would minimize tip deflection. So even though we were trying to induce, or be able to measure, tip deflection or part deflection, we still employed a machining strategy that would minimize it. So we did the first half of the blade. So this is the roughing operation. Then we went into semi-finishing the top half. Then we go into operation 4, which is roughing the bottom half. Then again, for operation 5, we go into semi-finishing the bottom half. Then we switch over to doing a roughing operation for the platform, the outer surface of the platform, so the side surfaces. Then we go into finishing the outer surfaces of the platform. And then we transition. Operation 8 is the finishing the top of the platform. Then we go into operation 9, which is the full finishing operation for the blade. So this is going from tip all the way to the root of the blade. And that's going to be important, so keep that in mind. We're always going from tip to root. And then in operation 10, we're finishing and just doing a final machining on the tip so we can get that dimension in. The end result is the bottom right blue, what we call the in-process workpiece in Siemens NX CAM. And this is, if we did a deviation map in NX, which we're able to do, it essentially has 0 deviation, right, from the CAD surface. So this is how we verify that we're machining down to the surface that we want to machine down to in an idealized environment. We set up our inspection points like this. So on the suction and pressure side, you can see that we have points 2 through 16 on the suction side, and then we have points 9 through 31 on the pressure side. 19 through 29 on the pressure side. And the way that this is set up is point number 2 is, point number 17 is on the opposite side of point number 2. So, and point number 18 is on the opposite side of point number 3. So if we were to take the deviation from point number 2 and point number 7 and add them together, we're essentially calculating the thickness of the blade at that point. And that's important as I get into the inspection results. Just keep that in mind that we're not just doing surface deviation, we're getting the difference in the thickness of the blade. And that's to account for any, is to help visualize the total deflection and not have you look at just one of the components of the deviation. For this experiment, we used I'm showing a picture here of a 227E semantic edge device, but we use a 427E semantic edge device. This is the Siemens product. It connects to the Cinemeric 1 control that is on the TRAK machine tool. through the X2 port that you see there on the Edge device, and the X1 port on the Edge device. These are Ethernet ports. The X1 port goes out to our network. The Edge device is very capable in terms of, in terms of its capabilities. It's an industrial PC. It has its own firmware. It has different Edge applications that you can install on it. One of the points that I want to make in this slide is the ease of connectivity, right? There's no wiring. It's really just an Ethernet cable from the X120 port on the CMARTE Edge to the X2 port on the Edge device. It's a device that you purchase, and it literally takes, minutes to install on the machine. I'll go back to this one slide here. When you're connected to your network, if you have internet access, you can connect to Siemens cloud platform called Insights Hub. And on that, you can actually access your Edge device. And you can install applications from Insights Hub, which is essentially a large, it's a collection of different applications that Siemens posts up there, that other contributors can post up there, and that you can download onto your Edge device, and then you can log into your Edge device and install it on the Edge device itself. One of the applications that we used for this particular demonstration was a software called Analyze My Workpiece Capture for Analysis. What this software allows us to do is to select specific variables that we want to record off the CMARTE 1 controller. So on the TRAK machine tool, we have 4 axes and a spindle. So those 4 axes have, obviously, they're driven by a motor, and the spindle motor itself, it gives us a total of 5 motors. And for each of the motors, we have several variables that we can track. One of them is load. Other ones are encoder position. Other ones are, current. And others. I'll show you the parameters that we're actually tracking in the next slide. But another capability of this particular Edge application, Capture for Analysis, is that it allows us to define triggers. So what's important here is that if we're machining, you saw the different operations that we go through to machine the particular airfoil. What we want to do is segregate the signals. So what's important here is that if we start a manufacturing operation, all of those operations are going to complete on the machine. It'll automatically go and change the tool out for the appropriate tool for the operation, and machine, finish machining to the final geometry that we saw for this experiment. But what we want to do is we want to make sure that we don't have one long signal capture. So we don't want to just start recording data at the beginning and stop recording once we're finished machining, because then we have to have some way of breaking up that signal to then correlate that with post-inspection results. So what the Edge device gives us the capability of doing is actually defining triggers. And the way we define the triggers is in Siemens NX CAM, when we generate the tool paths, for each tool path, we have a start and end condition. And the start and end condition, we can add a trigger phrase. So that trigger phrase, once you post out that program, that trigger phrase shows up in the G code as a commented line. And there's a specific phrase. You can have it be whatever you want it to be. In our case, we name it, the operation number. So op1, op2, op3. And we append an S or an F. So op1 S is op1 start. Op1 F is op1 finish. So in the Capture for Analysis software, if I define a trigger to say that I want to have a separate directory where I'm going to store all my recordings for that one operation, operation 1, when you hit op1S, start the data recording on all the variables I want to record and save it to that particular directory on the Edge device. Then when I hit operation 2, it'll store it in its appropriate directory. This is very important, and you'll see why when we get later on down in the presentation. And then we have the management side, so we can activate and manage capture jobs. So the jobs, contain our conditions for recording. One of those conditions being the triggering capabilities. So very capable software gives us all the options that we need for precise control over what's recorded when and how it's organized on the edge device. The edge device itself has a solid state drive on it. So ours, the 427E, has a 500 gigabyte solid state drive. When we're doing data recording, it records it right onto the edge device. So the capture for analysis, the other capability of the software is with this active and managed jobs, the item 3 there, it allows us to export that data out as a JSON format that we can then bring onto our computers and process later. Other edge applications include monitoring applications. There's AI inferencing applications. And these other applications we're going to present to you at later demonstrations. So this is demonstration 2 of 8 for this particular federal program. And in this one, we're just focusing on capture for analysis. These are the high frequency parameters that we were collecting off the machine. Again, it's 5 motors, and for each of the motors, I think we're getting about 12 parameters each. The important thing to note here is that we're getting those 75 parameters at 500 hertz frequency. So it's a very high frequency. In fact, we can go up to 1,000 if we wanted to. What that means is every 2 milliseconds, we're getting 75 data points. It's very rich data. The more data you have, the better it is in terms of coming up, and you'll see this in a chart later on, to correlate or to understand what parameter affects what when we're doing causality analysis. Again, more on that later, but 75 parameters at 500 hertz is what we're able to capture on the edge device. So here, this is just showing, having come up with the operations, the manufacturing operations. Now we're using Run My Virtual Machine on the left there to verify the program, but we also use the program for causality analysis. In this case, we just wanted to make sure that the tool paths, once posted out of Siemens and running on the Cinumeric kernel within the Run My Virtual Machine, that it would produce the blade geometry that we're looking for, right? You can come up with a CNC program, post it out, and if you run it on your machine, if you have any discrepancies between your post and the physical setup of your machine, the geometry, it may not come out right. And then the video that you saw playing on the right was the real machining operation on the machine itself. So we produced 23 blades in total. And what I'm showing you here is a compilation of the inspection results. Don't worry about the table on the left. We'll go more into that. Really just focus on the image that you see there in the center and the actual deviation mapping on the right. So what we see here is that we have more material on the tip. So the physical cut part has more material there. This deviation map is essentially showing us the difference between the nominal, the CAD surface, and the as machine surface of the part coming off the machine. So if we go on that, on the heat map on the right, if we go up into the reds, it means we have more material left on the surface. If we go down into the blue, that means we have less material. But one thing that you'll notice is that we actually have about 3 thousandths left on the blade surface itself near the platform, so towards the bottom of the blade. And as we go up, it actually goes up into the, almost 30 thousandths of material. So this is expected because we left the tip free, right? We know that we're going to get some amount of deflection. The tools that we chose to use were all solid carbide, and the material that we're cutting is Ti-6-4. So likely the tool is not going to deflect, right? Or if it does have deflection, it's going to have very little deflection. But the workpiece is going to show more of, it's going to take more of that, you know, it'll deflect more because of the forces induced during machining. So, but what's also interesting is that towards the platform, we're not at nominal. We're still off by close to about 3,000. So that's very interesting. Why is that happening? Why are we getting, you know, we can kind of think what's happening at the tip because of the physical circumstances of machining. But I would have expected to be more, you know, intolerance towards the bottom. So before we go into, you know, more analysis on what's happening there in the deviation, let's take a look at what we have set up as an overview architecture. And I call this an AI-based digital twin architecture. Really, all of what we're showing here is how everything is connected, how we're capturing data. At the bottom left, that is our model-based definition. And we use model-based definition to create the program, the operations to produce this part. Then we have stock material. Now, one of the things that you can do with the stock material is you can take simple measurements on it, length, diameter, right? If you're getting stock material from different sources or they're from different batches, you want to record any differences between the stock, because that ultimately could be one of the causes of deviation. And not only the deviation, but causes of signal changes when you're recording signals. So for example, if I have a stock material from a batch that has a diameter of 1 inch, one and a quarter inches exactly, and I put it on the machine and I do my roughing operation, I'm getting the loads, right? I'm getting signals from a machine that's recording load on the spindle. Now, imagine if I had a stock material from another batch where I was, let's just say, 1 inch, 300 thousandths, right? I'm 50 thousandths over my material. That's a bit of an extreme exaggeration. But when I put my stock material in the machine and I go to perform my first cut, the tool is actually engaged a lot more. And so I should expect to see the signals, the load on my spindle to be higher. So this is one of the reasons why you want to take any measurement that you can on your stock material before it goes into machining, because that data point or those data points really help to understand what's going on. So you can take a 3D scan of it. If you can get a quick temperature measurement on it, any amount of measurement that you can digitize, right, and provide to the AI machine learning system that you see there up top is beneficial. Then the edge device connected to the CNC machine. Of course, we have real-time data being collected at a very high frequency, and that's going to ultimately be the data that's recorded on the SSD on the edge device will eventually, go up to for model training. And then we have post-inspection, right? So once the parts are produced, we want to put them on a inspection equipment that can provide digital information. Those control points that I showed you before, on the 3D scanner, we can scan the entire surface, we can align it to the CAD, and then based off the datums, and then we can extract the deviations of those control points, as you saw in the inspection setup. Those deviations then go up into the machine learning solution. The important takeaway from this slide is digitization. You want to have a digital signal, digital source for as much of the condition going into the machining as possible, and then also coming out the results of the machining operation through inspection. Even if you're taking caliper measurements, if you can provide those as digital sources, it's beneficial. So just to recap, the inputs to the AI system, right? We have our manufacturing machine, the TRAK VMC10si, and we have an edge device that's providing data, rich data, to the AI system. What is that rich data? It's the data collected from the edge device, and it's the post machining inspection results. So those are the two data sources going into our going into the AI system. Once you train a model, so those two data sources are used to train a model, and Danny is going to present exactly what that means and the results of that model training. But once we have that model, we essentially have a file, right? And that file essentially encodes that file encodes it's essentially a digital twin of the manufacturing process for that particular part, right, that we're training all of. And what I mean by that is, if we were to now produce blade number 24, and we stream, instead of collecting the data on the edge device, we stream that data to the model. That model will then predict what's going to happen in the next few seconds. And based off of that prediction, we can make corrective action control. So this is why I say digital twin of the specific part, in this process. But more to come on that. Physics-informed AI for CNC corrective action control. When I say physics-informed AI, causality analysis is very important. We need to understand what's causing, what are the sources of deviation, right? I'm going to talk about this more later, but third wave is a software solution that we're using to essentially simulate the cutting process and understand how much distortion we're expected to see based off of the stiffness of the tool and the material that we're cutting. So we can get a lot out of that, but this is that physics-based model really helps us to understand what's causing some of this deviation. But here what we're showing is we've got the machining operation, real-time data being collected, and then normally we would have gone the route of using an algorithm called LSTM. It's a long short-term memory algorithm. It's really good at forecasting. So if you have a number of signals, it can kind of predict what's going to happen in the next few seconds. The more far out you go, the less accurate it gets. And then we would have used that forecasting that forecasted signal to send into, for example, a random forest multivariate regressor to come out with the predictions of the control points. But in our particular case, this isn't going to produce as good of a result because we're compounding error. So the LSTM algorithm is going to have its accuracy, right? It's not going to be 100%. And now we're feeding that inaccuracy to another algorithm that itself isn't going to be 100% accurate. Instead, we're going with Dr. Imani's retrieval prediction algorithm. And from here, not only can you do signal processing, signal forecasting, but also prediction of deviation. What we do with that data then is, since we now have the prediction of possible deviation, we want to go into causality analysis and then corrective action control. Before we go into that, I'd like to bring up or invite Danny up to talk more about their algorithm and the results that we got from the data that we collected on a machine from machining these 23 parts.
All right, hi everyone. My name is Danny. I am a second-year PhD student under Dr. Farhad Imani, and today I will be presenting the multivariate time series retrieval augmentation prediction for advanced manufacturing. In this case, for the blade made of titanium. So for the concept of this presentation, I'll first talk about the model overview. Then I'll talk about the data preprocessing that I had to do, which leads into the database generation for the retrieval part of our algorithm. And then I'll finally discuss the results and analysis and then final conclusions about the project. So for the model overview, we first have the manufacturing, and then that manufacturing data is captured using the edge device. From the data that we've captured, we have to do some pre-processing. We can't directly work with the CSV files on the data itself, but after we do pre-processing, we can give that into our model for that prediction step. And how we actually pre-process the data is we generate a database of all the signals that were captured, and then from that database, we retrieve the most similar information correspond to the signals we want to test. And then from that similarity, we have associated deviation measurements that we can use for the final prediction. And I'll go more into that in a little bit here. So from the data that are signals, so we have here some examples of the signals that were captured. So we have load 1 to 6, skipping 5 because it's the 4-axis machine. So you have the X, you have the Y, you have the Z and the A and spindle that were captured. And since we are working with 500 Hertz, that is relatively a large amount of data that we're working with. And so we decided to downsample the data by 2 just to make sure that it's more manageable in order to use. From this downsampling, we implement a sliding window of 250 data points, which is around half a second, with a stride of 50 steps over, which is about 0.1 seconds. And then from this extraction, we encode that using a transformer-based encoder, which is pre-trained on time series data. And so how we do the actual windowing is we define a window here is 250, and we stride it over. So we move it over the signals here in order to basically extract that information. And the reason why we do a striding rather than just segmentation without overlap is we want the before and after information, because the signals or variability we see in the past and in the future can impact the final prediction, and we want to take that into account as well. So after we extract all these windows, we have to do our database generation. How we do that is we use something called a Chronos encoder. So the Chronos model was a pre-trained model from Amazon that is publicly available. So everything we've used is open source. And so you don't have to pay for any of this technology that we're using. You just have to download the respective packages, and you're able to implement this on your system. So take, for example, we have this window here called window 1. We put that into the Chronos encoder, and that encodes it into these many different vectors we see. The vector size of the final resulting information is around 512 dimensions. And the main thing we want to concern about is the context tokens. And so this is Transformer use something called tokens, which splits up information. In terms of large language models, a token in the large language model is like the word segments we see, but in this case, the tokens we see here are the individual time segments or the variation we see. And these context tokens is what's being used in order to do that prediction. Because if we see similar tokens in our data, this means that the prediction of forecasting, for example, we can predict what's happening next because we see similar patterns in the variability. So we do this for one window, but we have to do this for all the windows and across all different channels as well, and across our multivariate different process parameters. And so we have a n number of windows and d-dimensional vectors for each of our windows and our signals that were recorded during this process. And so for the actual database generation is we want to store all the vectors that were generated using this Chronos encoder. And so how we implement that in a way that's more efficient and quickly for our prediction is we use something called Facebook AI Similarity Search, or FAST. So this is another open source library. This is how we can generate our database for that quick and efficient similarity check for that prediction step. And so after we encode our data, we use this FAST library in order to generate our database. And so that is our database. And we do this for two different operations, which is the blade profile finishing and the shoulder front finishing. And the reason why we chose these two different operations is because we have some sort of mapping with regards to this operation and the final deviation result, which is what was reported after the process was done. And so to summarize the database that was created, we have three different signals we focused on, those being load, encoder position, and control position across the 5 different axes, so X, Y, Z, A, and spindle. And then we have 2 different operations. And so we have a summary of how many vectors that were actually generated per signal per axis, including the spindle. So for the blade profile finishing, we have around 50,000 vectors for a database, and the shoulder front finishing, we have around 13,000. And then we have, and if you extrapolate this across 10 different parts and 15 different signals, we have around 3.2 million vectors that we need to compare to for our final prediction step. And so after we do the database generation, we want to test them all. And how we do that is we have recorded time series signals, and we want to map this to the specific control points that we want to test from. And so say, for example, we want to do the blade profile finishing, which we're trying to map it spatial temporal mapping. And so we zoom in here for these 6 different test points. From the signals recorded, we implemented a uniform distribution regarding with the time to the actual test point we want to test. And so we split it up in equal segments. So each time series segment is associated with a specific test point. And then from here, we can make the predictions. Because the reason why we want to do this is a time at the beginning is not going to be indicative of the test point at the end. And so we don't want to do extraneous predictions because it's not linked to a specific test point. And so for the actual time series prediction, after we have this database structure, we have 5 main steps in order to do that test point prediction. And so the first step is, given our time series segment that we segmented associated with a particular test point, we do the same windowing. So we do the same 250 window size with a 50 point stride over the signals, and then we do the same encoder. So we use the same model to encode because we have to use the same model in order to do that similarity step. And then from each vector that was embedded using the Chronos encoder, we perform a similarity check over the whole database to figure out which of the signals or which of the parts is most similar to the signals we see. And then from these signals, we can do that prediction using a weighted prediction measurement. Because the parts that are most similar, we know a respective deviation value associated with that part and test point. And so we do a weighted prediction measurement, prediction, in order to actually predict what the deviation should be from the signals that we see. And so we see here from the results of just predicting part 15 with load, we can achieve really good results. We are actually have a very small MSE values. I'll flip through the 3 different signals until the end for the summary. But if we compare to encoder position, load performs as actually much better compared to encoder position. And if we compare that to actually control position, if you blink it and miss it, you actually don't really see that much of a difference. And from here, we can discern which signals are most important, because we're collecting like 15 different process parameters, but not all process parameters might be important for the prediction step. And so this is one step in order to figure out, from all the parameters we have in the different operations, can we discern which process signals we should focus on for the most accurate prediction? So we're not doing extraneous calculations or making extraneous database, and which can speed up computational time as well. And so this is the average MSE across all test points and across all different signals where we're tested. Now we see here the main takeaway is that the load signal achieved the lowest MSE scores compared to encoder position and control position. There are some exceptions around some different test points, such as 28, 29, and let's say 36 and 38, where load performs less. But overall, this signal was found out to be the most accurate in terms of predicting that deviation measurement. And then we can also see the MSE per part as well. So we have the 10 parts that were predicted here. And again, we see that load performs the best, with the exception of part 11, where load is around 2.5 times greater in error compared to the rest of the signals. And then the same thing with shoulder, we still see similar results compared to the profile, where load is the overall most important. And the reason we care about which signals to choose is here we have the ranking for the first 6 test points. So from the first 6 test points, I recalculated the MSE for each of the individual signals rather than using all the signals together. I did an individual prediction for each of the signals, and then I ranked them in terms of how accurate these predictions are by using a particular signal. And we see here that the lower the score, the better the prediction was. And so we here for test point 1, if we use just load 4, that gave us the most accurate prediction, and then we can rank all these other 15 different signals as well. And this gives a good indication of which signals to choose. So for test point 1, depending on the spatial geometry of the part, for example, we might not want to focus on control position 1. And so we can remove that signal and just use the most important signals for our prediction. And this is repeated across different test points as we see here as well, where we see the shifting of which signals to focus on depending on the location of the test point itself. And so to conclude this algorithm and presentation, we found that load signals showed overall the greatest accuracy in prediction across the test points and the 2 different operations we tested. We showed that encoder position and control position provided similar or nearly identical results, indicating that the features we see from these signals are very similar to each other. And so we can tend to focus on one of these signals rather than all of these signals in our prediction step. And then if we do the actual computational time, when we're doing the actual testing, per each window, per each signal, it takes around 0.72 seconds, so less than 1 second in terms of time in order to do that prediction. And then in terms of how many computational resources, I have it here, but it takes around to load the data set and to run the model, it takes around 14 gigabytes of VRAM. And so this is very applicable for using just one graphic card. You don't need a high performance computer in order to do this prediction. It's a very lightweight alternative to high computational cost. And then the future work I've shown a little bit here is focusing on signal selection. And so here we use all the different, all 5 axes for the different signals, but we have a ranking of which signals to choose from. And so we perform a weighted prediction score corresponding to the most important signals. This should, in theory, increase the accuracy that we see. And so we're not using all the signals together. And this also would increase our computation time. And then although we're going to be implementing the physics base from Nasir side, where we have the actual deflection prediction using simulation results. And so we can incorporate that in as well with a large language model in order to reason about which corrective action to take. So we can use this for real-time process correction by updating the parameters that we use for these machines such that we minimize the deviation. All right, thank you.
Thank you, Danny. I really appreciate the insights there. I just wanted to stress a point that that Danny was making, especially with the number of signals that we're capturing. A lot of the times the question here is, why am I going with reporting 75 signals? You may there are systems out there that look at overall system horsepower, adaptive control units, and others, and certainly those are viable solutions. But the value here is in understanding what signal is most important to calculate the end result of the deviation, the prediction of the deviation. So as a simple example, if we have a spindle motor turning a very small diameter drill, let's say it's an 1/8-inch drill, and we're plunging into say aluminum 6061. The amount of load that's on the spindle motor just to rotate it is, especially if it's a larger motor, it's significant. You can see it go up as you rotate the spindle. So if you then plunge that tool to do actual cutting, to drill a hole with a 1/8 inch diameter hole, the amount of change in the signal might be very little to negligible. Whereas if you had a larger diameter drill, let's say you went with a 1/2 inch drill or a 1 inch drill, and you plunged into the aluminum, you'd see a bigger change from the load incurred from rotating the spindle to the load incurred in rotating that tool through the material. So what's important to note here is that I can't use the same signal. I wouldn't be able to necessarily use load when I'm machining an 1/8 inch hole, as opposed to if I was machining a 1 inch hole, because the signal changes may not be relevant enough. Whereas if I capture other signals, I have other data points to look at to see if those have a higher weight. So I just wanted to make that importance there, and a understanding of why it's important to capture as much data as possible, because then you can perform the kind of analysis that Danny so nicely showed in that color chart. Now we're getting to the point of, what do we do with all this? How is this great for manufacturing? How do we use this algorithm and the output, the accuracy of the predictions of the deviations that the algorithm output, in terms of controlling manufacturing variability? Let's first look at, total deviation. What are the components of the total deviation? What comprises the total deviation? We'll look at how we can break out some of those components through simulation, again with third wave solution distortion, to take a look at workpiece deflection. We can look at any pathing deviations through the digital twin through Run My Virtual Machine. And then we can look at tool wear, but instead of measuring tool wear directly, let's look at tool wear measurement through statistical analysis. This way, we're looking at a more practical application of these technologies where you don't have to have a science lab to apply this. You don't have to take your tool off the machine and measure it under a very high resolution microscope. You don't have to, go through various different cutting trials to try and segregate the possible causes that are contributing to total deviation, right? You can just go ahead and machine your parts, collect the data, and then process that data as is. So this is why we set this up in this way, because it's more adoptable by current manufacturing processes where you don't have to have anything extra, just an edge device. Your post-inspection results in a digital form, and then the algorithm. So what are the causes of the total deviation that we saw in the color and the heat map that we saw on an earlier slide? On the bottom there, I'm showing total deviation equals pathing deviation plus deflection plus tool wear. We would have normally added other sources of deviation, such as tool deflection, vibration, heat, temperature. But using our engineering judgment and the setup of this particular experiment, we know that we can constrain it to these three sources. Okay, so pathing deviation we can extract through simulation using the digital twin. What the difference between the digital twin and the physical environment is that in the digital twin, you have the exact controller logic of running your virtual machine to cut the part. But what you don't have is any tool deflection or any workpiece deflection. So what we want to be able to do is run the program, produce a virtual part, export that part out, and inspect it, like we normally would with any part that we would have scanned on the scanner or any other measuring device that you would choose to use. That would give us any pathing deviation, differences between either our post or the difference, any differences that we have between between the physical and the digital world, the digital setup. Then we have our workpiece deflection. We can extract that through simulation. So we have physics-based simulations that we can run, and we can see how much deflection would be incurred in the titanium material induced by the cutting forces itself. And then we can take a look at tool wear. I put measurable down there, not physical measurement under the microscope. Again, this is through statistical analysis. So just a little bit about the tool orientation. It's important here because if you want to understand not only the sources or the causes of deviation, but the mapping to the corrective action. And it's very important to understand the condition of machining and specifically the tool orientation, because tool wear is one of the causes of deviation. So we want to know where the tool wear is happening, and we want to know what do we compensate? Is it typically you would just do a tool radius offset for tool wear, but in this case, it's going to be a little bit more, because the picture on the left there is showing that we're machining at a rotated angle of 25 degrees. The reason for that is that we don't want to be cutting right at the tip of the tool because we want to have some surface feet per minute. So we're cutting a little bit off the tip so that we have a radius there. And then on the picture on the right, this is just showing we're using a 4-axis machine. So it's going to be normal to the x-axis, the rotation axis here in this case. So getting into where we're cutting on the tool, we just want to be able to understand the component breakup between tool length and tool radius for the purpose of compensation of the tool wear. So what's happening here is because we're machining at a 25-degree angle, our effective tool radius is a component of our actual tool radius. The actual tool radius would have been at an angle of 90 degrees, right? Right at the corner of the tooth. This is the total. If our contact point was here, we would have been at half of the diameter of this tool. The tool diameter is a quarter of an inch. The tool length itself, again, we have an effective tool length because this distance is not the same as the projected point of where you would have been, or out here if you were machining on the very edge of that tool. So this is just showing that we're just breaking out the components and we're getting the compensation for the tool radius and the tool length on the image that you see there on the right. Now into understanding deflection. This is, again, a piece of software from Third Wave Solutions. The product here is called Distortio. It's a function within their main product called Production Module. And what I'm doing here is I'm going to run an analysis on the deflection of the tip using the position of the tool as you see in the images on the top. So control point, 1 all the way to 6. And then I have the mapping to the control point to the inspection control point number. So what we do here is the tool path, the tool, the actual workpiece, the materials, everything is defined in NX, right? Because we're starting off with model-based definition. And Third Wave has a plugin to Siemens. It's a button click to export all that data out into production module. So I don't have to do any setup. All the tool paths go in, material conditions, and all I really have to do in a production module is click a button called Analyze Tool Path. And what that does is it essentially runs FEA in the background, and it calculates the forces, the cutting forces that are induced while machining this particular material. With those cutting forces, we can then calculate distortion on the part. If we take those cutting forces at a specific point in time, and those points in time being these points that I'm showing up here, and giving that force information, that force profile to Distortio, that can then run distortion analysis. So what we're seeing here at the bottom is that the results of the distortion analysis. So here at control point 1, we're deviating by 5 thousandths. You can see here it's about 5 tenths in the middle, so on and so forth. So it's a significant deviation. 5 thousandths is quite a bit. This is just showing the force graphs that we get out of analyzing the tool path and running the FEA. What we're seeing here on on this particular slide is tangential force versus time, and chip load per tooth versus time. And the two, the distinct, shapes of the graph are to do with, machining the suction side and then the pressure side of the blade. So you can see the force profile there. Same thing, similarly here, we have the radial force and the axial force. So the radial force would be the force induced along the cutting direction, and then the axial force is through the tool. And then this is just showing a little bit more of some of the other force information that we can get. So we have a radial depth of cut versus time, an axial depth of an axial depth of cut versus time, and then the associated forces. Through analysis, so having cut 23 parts, we're going to take parts 4 through 20 to now run statistical analysis to understand and break out some of the other components of the deviation. So through simulation, we've gotten deflection of the workpiece. We're assuming zero tool deflection, but we do want to calculate what is the pathing deviation and what is the tool wear percentage. So what we're doing here is, again, if we go back to the beginning, I have the image there on the right. That's the reference. Control point number 2 and control point number 17, the total deviation is added. So what our inspection software does is it takes the CAD surface at that point and it shoots off normals from that particular point in either direction. And whenever it hits the measured data points, it will give you a positive or negative deviation. So if the surface is inside the CAD, it will give you a negative. If it's outside the CAD, it will give you a positive. Again, that red to blue color plot. But if we add them together, we're effectively getting the thickness across those 2 points at that point on the blade tip. So what we do is we get a surface deviation by halving the total thickness. What we're doing is we're equally distributing the deviation. The reason we're doing that is by doing it this way, we're effectively compensating for the distortion analysis, for the distortion of the part, because we've already got that through simulation. So now we're just looking to get, and the distortion as it shows up in the inspection results is going to be a positive deviation on either side of the blade. It's not going to help us. If we had a distortion where the distortion is happening in real time, and because the blade is rotating, it's distorting always in the negative Z direction. And so therefore it causes a positive deviation on both surfaces. And so we're running the analysis this way to basically eliminate having to look at distortion altogether. So what we do then is we look at the standard deviation of the number of points here. So we're taking, for example, on this check, point 4 and 19 give us the thickness along the leading edge. Point 3 and 18 give us the thickness along the stacking axis, and point 2 and 17 give us the thickness along the trailing edge of this particular airfoil shape. And we're looking at all the data across the 20 parts. So the standard deviation, the only thing that's really causing the standard deviation is tool wear, because we're having to swap out tools every 2 to 3 parts because the spherical end mill that we're using for the finishing cut is wearing down. And so we're associating standard deviation to tool wear exactly because we're in a position where we've already extracted out, again, the distortion. Pathing deviation comes in by run my virtual machine, exporting out the produced virtual piece and running the inspection. And what we saw was we were getting a pathing deviation of 8 thousandths right out of the box. So we were, what we do is we take the total surface deviation and we essentially minus the deflection right, the pattern deviation, to verify that the tool wear is eventually going to end up being exactly half of the standard deviation at a standing. The reason it's half is because we have a diameter and we're looking at the radius. So this is some graphs of the tool wear and tool deflection mapped out as we go from tip to the base of the blade here. What you notice here at the top, and we're looking at the components of the total deviation at the leading edge of the blade, we see that deflection is quite high at the tip and then slowly decreases, in fact goes to negative as we get to the base. Conversely, the tool wear starts off small but increases as we go to the base. This makes sense because we start at the tip and machine down to the root. Similar trends for stacking axis and trailing edge. What we can do with this data is we can calculate the percentage range within which we're seeing this, seeing the behavior. So at the tip of the blade for control points 1, 2, and 3, we're expected to be within a 0 to 10% range for tool wear for total deflection. Whereas in the deflection percentage range, we're at about 40 to 60% deflection range at the tip. Tool wear increases as we go down, and deflection decreases as we go down. This is important because this gives us a mapping of correction of what to correct for. So if we now look at, okay, we've broken out the components of total deviation. We know that we're getting deflection, we know that we're getting tool wear, and we know we have path and deviation. How do we correct for this? What's the mapping between the cause of the deviation to the parameters that we must change on the machine to compensate for this? So in Distortio, what we can do is we can run multiple simulations with varying speeds and feeds. Mostly what we do is we change the surface feed per minute and the feed per tooth. What I'm showing you here is the result of before and the final strategy that we ended up picking. We could have gone further and done more simulations, but this produced actually a good result. So we went from a spindle speed of 917 RPM up to 366 RPM, 3,667 RPM. And we dropped the feed rate from 22.8 inches per minute to 15 inches per minute. What this does is it decreases your feed per tooth, and it increases your SFM. It does increase the temperature at the tool part interface, but it's still below that temperature, and the temperature we get out of production module when we do the analysis. I don't show the graphs of the temperature data, but we're still below the recommended temperature cutting condition for the tool. And so what we end up with is if we're taking off a significantly smaller amount of material from the titanium, it ends up that the forces are reduced significantly. In fact, in order of magnitude, we went from 5 thousandths to about 10 thousandths here. So you can see that the forces are reduced. And mind the exact, we add a multiplication factor to show that distortion more. So this is at I believe at 50x, and this is at 100x. So here, essentially what we're doing here is we're figuring out that in order to compensate for workpiece deflection, we need to increase our spindle speed and decrease our feed rate. So if we wanted to have even further compensation, we could adjust those two parameters. This is just showing what you saw visually in a graph side by side. You can see that we're significantly decreased in distortion. And then this is just showing the results of the actual loads, the cutting forces, having gone up in the spindle speed and decreased in the feed rate. What we also did was we used production module to optimize the tool path. We You can see that there's some force spikes there towards the end of the program. A force spike that high could actually break could chip a tooth on the actual tool. So to increase the tool life, we actually want to minimize these force spikes that happen. The idea here being that if the tool sees fluctuating forces, it tends to break earlier than if it sees a constant force as it's machining. So this is just showing the results of the optimization. This is for the platform machining, and that is for the blade surface. What you're looking at here at the graph at the bottom right, the green is the after optimization, and you can see that it doesn't increase past a certain amount. So we limit, we tell the optimizer that we want to limit the tangential force at about 5 pound-foot. Pound force. And same thing here, we limit it to the same amount. Effectively, what this does is it increases our tool life. And so here, what we can do is, we know that for workpiece deflection, we have to adjust spindle speed override and feed rate override. For tool wear, we need to adjust for tool radius offset and tool length. We need to compensate for the tool length. And further, we know the component breakdown because we know we're at a 25-degree angle. So what we do is we use the function on the CMARIC control. The Siemens gives you R parameters. These are variables that you can use in your G code to apply a multiplication factor. What I mean by that is, a multiplication factor. So here in the G code, what you can see is the way we use the R parameter is that we associate or we multiply the spindle speed here with a particular R parameter, in this case R1. For the feed rate, we're multiplying it by R2. And what we can do is we can use an OpenCUA connection to the controller because the controller has a OpenCUA server on it to send or to control that R value over the using the node address that you see at the bottom right. And so the result of all of this is compiled here in this slide. What we see on the left is the baseline that we started off with. We corrected for pathing deviation by looking at the differences in our virtual environment to the actual cutting conditions on our machine. And we adjusted a Z offset to compensate for that slight deviation that we were seeing out of the machining program. Then we used third wave distortion to calculate workpiece deflection and compensate for workpiece deflection by adjusting the spindle speed and the feed rate. And then we compensated for tool wear, eventually getting us to within plus or minus a thousandth of an inch. This particular experiment went from collecting data on 23 parts and applying it to part number 24. In our upcoming event, we're going to show you real time, as we're machining, how we're compensating for all the causes of deviation. The true takeaway here is, what is the impact for your company? What is the impact of manufacturing? So if we take a look at the costs associated, right, and we extrapolate across 100 parts, we produce 23, but we take it across 100 parts. If we were to, with the traditional fashion, without any corrective action control, our tooling cost is about $5,445. Our machining time, the cost associated with that is about $30,000. Material cost is about $10,000. So that, and then the rework cost. So if we were to not apply corrective action control, every number of parts, the part would come out of tolerance. And we would have to rework that part, remachine it back down. There's tooling costs associated with it, machining time, and that cost comes out to about $11,000. Our total cost there is about $57,000. with the digital twin optimized workflow, we're saving 35%. So the impact to your manufacturing in only across 100 parts is literally 35% in total cost savings. So if you marry that with the savings, the time savings that you get with a model-based workflow that we presented in February, and the video of which we can make available to you if you missed it. If you combine these two, you're saving literally 80% of time in programming, and you're saving 35% of cost in manufacturing parts by having this supervisory control that basically guarantees that your parts come out good every time, without having to sacrifice additional machining time. So future work, as Danny also had expressed, we're going to continue to refine this process. Again, we're going to want to show you how this process works in real time. So stay tuned for an upcoming event. It's likely going to happen in 2026, not this year, but 2026. We have other events scheduled for the rest of this year, but we'd love to see you back here to see more progression in this